Hello students, welcome to chemistry class. So as you can see on the screen, today we are starting the unit number 5. The name of this unit is solution, and this unit is very important for your JEE mains and advance. Okay, so let's begin without wasting any time. And to explain this chapter, to explain this unit, we have to follow a simple flow chart, summarized flow chart. I'll show it to you. Let me zoom out. Yep. So as you can see here, so we have a simple flowchart of summarized form of the chapter solution, and we'll discuss all these subtopics included in this flowchart along with some concepts, some examples, some formulas. Okay. So this chapter is divided into 4 to 5 parts. As you can see here, types of solution, solubility, okay, colligative properties, Raoult's law, different method to express concentration of solution, right? So these 5 subtopics are very important to understand the chapter solution. Okay, so let's begin. Let me zoom in for the better visibility. Yeah, so we are starting with a simple definition what solution is. Okay, so to explain the solution, suppose I am dissolving a small amount of salt in water. I am dissolving 1 teaspoon or half teaspoon salt in 1 glass of water. So salt solution will be formed. Now in this example, yes, the amount of salt is very low, but the amount of water is higher than salt. So during the formation of solution, if you are taking two different components, or we can say more than one component which are different from each other, component having very less quantity is called solute, and component having high quantity is called solvent. So what we can say? We can say that solution is made by solute and solvent, or in simple words we can say the homogeneous mixture, listen carefully, the homogeneous mixture of two or more components, then it's called solution. Okay, so this is the simplest definition of solution which you have to remember from your side. Okay, now on the basis of state of solvent and solute, we can easily categorize solution into 3 types: gaseous solution, liquid solution, and solid solution. And remember one thing, in all these 3 types, the solvent is, the name is completely dependent on the state of solvent. It means if I am talking about the gaseous solution, the solvent must be gas in all the conditions. Solute may change, solute may be solid, maybe liquid, maybe gas, but solvent must be, listen carefully, the solvent must be in gaseous phase. Similarly, for liquid solutions, the solvent must be in liquid phase, and similarly for solid solution, the solvent must be in solid state. Okay, so these are the very simple key points, very essential key points which you have to remember from your side. Now we are talking about the gaseous solution. So as you can, as I told you earlier, in gaseous solution your solvent should be gas, but your solute may be gas, liquid, or solid. So suppose if we are mixing gas with gas, solute gas in solvent gas, then what should be the example? Mixture of O2 and N2, mixture of oxygen gas and nitrogen gas is the best example for gas solution, or we can say this is called atmosphere also. Atmosphere is a very good example for understanding the gaseous solution. Similarly, if you are mixing chloroform with nitrogen, You know that nitrogen is a very huge quantity of gas. It present in our atmosphere approximately in 78% ratio, right? And chloroform is a liquid. So you are mixing liquid in gas where gas is more. So gas will be your solvent. Okay. So you are mixing chloroform with water. This is the best example for explaining liquid gas solution. Solid gas where solid must be in less quantity. So camphor in nitrogen gas. Whenever we heat the camphor convert itself into solid to gas. This is called sublimation. So whenever camphor convert itself into solid to gas, gaseous molecules mixes with nitrogen, or gas particles, we can say camphor particles mixes with nitrogen gas. Okay, so these are three examples for explaining the types of gaseous solution. Okay, I hope it is clear to you. Next, moving on to the liquid solution. In liquid solution, as I told you earlier, all the solvent must be in liquid state, and solute may be solid, gas, liquid, or solid individually. Okay, now we are mixing gas in liquid. What should be the example? Oxygen dissolved in water, and all the aquatic life completely depends on this principle. Okay, so assume all the oxygen gases are removed from the water. All these fishes, all the aquatic animals will die suddenly, or not suddenly, we can say instantly. So oxygen is a very essential molecule for the living organisms like us. But we have to take this example in which solution? So we are taking this example in liquid solution where liquid is more, water is more, but dissolved oxygen is very less in quantity. Similarly, liquid in liquid, we are mixing alcohol in water. So alcohol is less and water is more, so ethanol dissolved in water. Okay, solid in liquid, glucose dissolves in water. The patient who are suffering from the dehydration, so doctors or physicians suggest them take glucose with water, take glucose solution. Okay, so glucose dissolved in water is a very good example of solid liquid solution. Now, next type is solid solution where solvent must be always in solid state. So the example in which gases are dissolved in solid: oxygen in palladium, liquid dissolved in solid, amalgam with Na. Amalgam stands for mercury. So whenever mercury dissolves or mercury reacts or combines with any other metal, it's called amalgam. Okay, so we are mixing sodium in mercury, right? So mercury is in liquid state, you know that. Okay, so if mercury is in liquid state, then sodium is a solid. So sodium is solid, sodium is dissolving in mercury. So what we can say, mercury what we can say mercury is a liquid which is dissolving solid, which is a uh, 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 dissolving the sodium which is in solid state. So actually what we are doing solid into liquid. Okay, simple. And solid into solid, copper dissolves in gold. Okay, in the process of making alloys, many different metals combines with other metals in different ratios. For example, if you heard the example of bronze. Okay, so bronze is made by copper, copper and other metal, that is tin. Okay, so during the formation of alloys, we have to take what? We have to take different metals in a different ratio. So we have completed the definition as well as types. Hope you are getting things in very easy manner. Next we are moving on the concentration terms. Concentration terms, how can we, what is the term called concentration of solution, and how can we determine this? Look, suppose You have dissolved 1 teaspoon of salt in water, assume that. Okay, now after the formation of salt solution, I have asked from you how many salt particles. Salt is, the salt is NaCl, you know that already, right? So how many NaCl particles are present in this 1 glass of water? So the methodology which determines, listen carefully, the methodology which determines the quantity, or we can say moles of solute. NaCl is a solute because it is in less quantity, water is in more quantity, high quantity, right? So the methodology in which we are determining the quantity, or we can say weight, we can say moles in the given solution, then this term or this method is called concentration of solution. Okay, so concentration is like a focus, right? But we are not discussing the focus, we are discussing the amount. So concentration is amount of any solute or any less quantity substance in the given solution. So we have different things, we have different methodologies to calculate the concentration in any solution. So we'll discuss it one by one. So we have different methods here. Yeah, the first method, as you can see here, the first method is mass by volume percentage. The symbol is W by W percent. Second, volume percentage, as you can see here, the symbol is V by V percent. Third method, mass percentage, the symbol is W by W percent. Next one, fourth, that is ppm, parts per million, parts per million. Okay. Fifth, that is mole fraction, mole fraction, fraction of moles in simple words. Sixth, normality, the symbol is capital N, capital N. Seventh, molality, molality. And number 8, that is molarity. So these are 8 different methods. Obviously there are some more methods also, but these 8 methods are relevant and essential for your JEE preparation in your JEE syllabus. Okay, so don't worry about the other methods, they are not essential for you. Now let me explain you to briefly. Number 1 is mass by volume percentage, W by V percent. It means we can calculate the amount of, or we can say concentration of solute, if we are taking weight of solute in given volume of the solution. So the formula should be W by V percent is equals to mass of solute in grams and volume of solution in ml into 100. And why 100? Because we are calculating percentage. Simple. Okay. If we face some sufficient time, then I'll discuss some questions also, don't worry about it. Now volume percentage, solute and solution both must be present in volume, both must be present in the form of volume of component in liter or ml, we can say, and total volume of solution also in liter or ml. But the unit must be same during the calculation. This is very important, remember that. This is not my rule, this is the rule of international system of calculation. Similarly, mass percentage, so W by W percentage, solute and solution both be in the terms of weight. So mass of component solution in grams and total mass of solution in grams into 100. Okay. Now parts per million, you know that we all are the new generations. We are living in the world of digital era, social media, and many times we scroll the YouTube and we see the views 1 million, 2 million, 3 million. So what is the meaning of million? So according to the um Indian calculating system, 1 million is always equal to 10 to the power 6 lakhs. 10 to the power 6, sorry. It means 10 lakhs. Okay, so what is the meaning of 1 million, or what is the meaning of parts per million? How many parts of solute or component is present in 1 million of any solution? Okay, so the simple formula is, and a very important thing which is written here, we use this method to find out the trace quantities of solute. Suppose I have one bucket, the capacity of bucket is 10 liters, and I have filled that bucket with water. So I have 10 liter of water, and in 10 liter of water in that bucket, I have mixed one fingertips of salt, or we can say only 1 gram. I am mixing only 1 gram in 10 liter of water. So this is called trace quantity of solute. Okay, so to calculate the trace quantity of any solute, we have to use parts per million method, and in this method the formula should be ppm equal to number of parts of components, how many parts are there, upon total number of parts of component of solution. Parts of solute upon total parts, it means parts of solute as well as parts plus parts of solvent into 10 to the power 6, because we are talking about the million, and 1 billion is equal to 10 to the power 6 particles or substances what we have. Okay, now the another thing is mole fraction. Suppose we are mixing solute into solvent and we are making the solution, then in that solution how many substances are present, how many solute we have mixed. Sometimes for making the lemon water, sometimes we mix lemon juice, lime water, right, lime water, or we can say citric acid, along with sugar, along with salt. Okay, so sugar, salt, or we can say lime juice is a solute, and all of these are mixed in water, so water will be your solvent. But after mixing all these four components, the whole thing is called solution, lime solution. Okay, so how many solute we have mixed in the solvent is called moles of different components, or we can say parts of different components, right? So we can say that in mole fraction we have to take ratios of moles of solute or solutes and total moles of solution. So mole fraction is simply the fraction of moles of solute or one component with total moles of all the components. Okay, and the symbol of mole fraction is chi. This is not x, this is chi. Chi. So chi is equal to number of moles of component upon total number of moles of all the components. So suppose, for example, I'm giving you one example. Suppose component A and B in mixing with component C, and after that we got a solution. Listen carefully, है ना? This is very important. So A and B components are mixed in C for making a solution, simple solution. Now if we want to calculate mole fraction, we can calculate the moles of A, chi A, mole fraction of B, and mole fraction of C. If we are calculating mole fraction of A, then moles of A upon total moles Na, Nb, Nc. This is called mole fraction. Similarly, if we want to calculate the mole fraction of B, then moles of B, moles of A, moles of B, moles of C. This is again mole fraction of B. If you want to calculate mole fraction of C, then moles of C upon total moles of A, moles of B, and moles of C. So this is the beauty of the mole fraction, that is we can calculate the mole fraction of every particle which is present in solution, every component which is available in the solution, in the following method as you can see on the screen. Okay, so this is what we can say, a very simple method, very easy method to find out the mole fraction of any component in the given solution. Now another one, that is normality. Normality is a very unique term, or we can say very unique method to find out the uh, what we can say, concentration of any solution, right? The statement is number of gram equivalents of solute dissolved in 1 liter of solution. Number of gram equivalents. Okay, how many gram equivalents of solute is present in the given volume of solution? Suppose we have 1 liter of volume of solution, right? So how many gram equivalent of solute is present in 1 liter of a solution is called normality. A normality is nothing but a term of concentration. That's it. So don't take it don't take this as a burden, because normality, what is normality? That is a concentration term which is used to find out the amount of solute. That's it. Okay, now the formula is capital N is equals to number of gram equivalents of solute upon volume of solution in liters into 100, into 100, sorry, not 100, this is a mistake, sorry, this is a mistake. Number of gram equivalent of solute upon volume of solution in liter, that's it. 100 is absent here, 100 is it's a misprint. Okay, now many students have asked from me, what is a gram equivalent? This is not mentioned in our notes. Okay, so we can calculate the gram equivalent, and gram equivalent is given weight of solute in gram. Okay, and equivalent weight of solute, that's also should be in gram. Okay, now what is equivalent weight? So we are digging deeper, right? So what is equivalent weight? So equivalent weight can be calculated as molecular weight or molecular mass of solute and its valency factor, or we can say n factor. N factor is sometimes given in the question, like for H2SO4. H2SO4 is an acid, so how many H plus it will produce in the solution, in the aqueous solution? That is 2H plus. So 2H plus should be 2 should be the N factor of sulfuric acid, right? So calculation of N factor is very easy, don't worry about it. Sometimes it is given to you in the question, so you can easily find out the N factor. Now the main thing is, how can we calculate N factor? So these 3 steps are very essential to calculate the N factor, normality. Okay, now next one, molality. How many moles are present, how many moles of solute are present in the given weight of solvent, given weight of solvent. See the definition, number of moles of solute per kilogram of solvent. So 1 kg of solvent, right? So formula is very simple. The symbol is also very simple, small m. So small m is equals to number of moles of solute. It should be in moles are unitless, sorry. Mass of solvent must be in kg. So again into 100 is not required here. So number of moles of solute upon mass of solvent in kg. Similarly, we have the last term of calculating the concentration terms, that is molarity, and the symbol of molarity is capital M. And that definition is very simple. How many moles of solute is present in 1 liter volume of solution? So number of moles of solute in 1 liter of solution, right? So capital M should be equal to number of moles of solute upon volume of solution, and volume must be in liter. Again into 100 is not required here. Okay, so these things are very easy, very essential also for your numericals. So we should learn this in very deep manner. You have to practice more and more For every concentration term you have to solve at least 50 questions. So 50 questions for each term, and we have 8 terms, so we are solving 800 questions, sorry, 400 questions. If you are solving 400 questions, then trust me, you can solve any type of question in future from the topic concentration terms. Okay, so because it is very essential for your JEE syllabus, if you observe the previous year questions, you can find many questions related to concentration terms: molarity, normality, mole fraction. Okay, so don't skip it, please do it. Now, next one, I hope this explanation is benefiting to you, so because this is very essential for the examination. Now, next we are moving on to the solubility. So as I told you earlier, if we are mixing, just wait. Okay, so if we are mixing salt in water, the salt will dissolve in that water. So what we can say, we can say that the solubility of salt in water is very good. In the other part, if we dissolve, if we try to dissolve soil in water, will it dissolve? Your first answer should be no. So what we can say, we can say that the solubility of soil is very low, or we can say very bad, in the given solvent or in any solvent. Water is a universal solvent, no doubt. So in water, so what we can say, if solute is dissolving in water, if solute is dissolving in water, we can say the solubility is good. Okay, so what is solubility? Solubility is the ability of solute and solvent for a proper interaction, which results the complete dissolution of solute in the solvent. It's a very simple or a very challenging definition, but we have to learn it, we have to remember that. Okay, now on the basis of solubility, we can observe the two different types in our syllabus, that is dissolution of solid in liquid and dissolution of gases in liquid. The first example was dissolution of salt in water is a very good example of solid in liquid. Okay, so we are observing the first case, solid in liquid. If you want to dissolve solid in liquid, you don't need to take pressure. Okay, so for the solubility, we have to observe two different kinds of physical quantities, that is pressure and temperature. So in solid and liquid, there is no need to pressure. Effect of pressure will not affect the solubility, in simple words. But temperature plays a key role here. How? Uh, let me tell you one example. Suppose we are dissolving sugar. Sugar is the best example for explaining this. Suppose we are dissolving sugar in water, and we have two kind of water. Number one, cold water. Number two, warm water. If we dissolve 1 teaspoon of sugar in each of these condition, we are putting 1 teaspoon of sugar in cold water as well as 1 teaspoon in the warm water. Sugar will dissolve in which kind of water? Hot water or cold water? Fast dissolution will happen in which temperature? Cold or warm? Your answer is warm. So this is the physical quantity which plays a key role for the dissolution. Okay, so in warm water, the solute, or we can say sugar, is dissolving faster than cold water. So what we can say, if we increase the temperature, the solubility of solid in liquid increases. Okay, so this is a very simple example which we have to learn from our side. Effect of temperature, obviously we can observe the effect of temperature. There are two kind of reaction, that is endothermic and exothermic. Endothermic reactions which required heat to dissolve, also for making the product, like sugar in warm water, right? So this is endothermic. and exothermic heat is released for the production of product during a chemical reaction. Okay, so in a simple word we can say, if we increase the temperature, solubility of solid increases in the solvent or liquid. Okay, okay. Now the second thing is solubility of gas and liquid. This is again a very simple thing. uh, Let me tell you one example. Suppose we are consuming juice in a juice center. Okay, and we are consuming that juice, we are sucking that juice with a straw. Okay, so we are sucking the juice, we are drinking the juice with a straw. If we blow the air in that in the juice glass, bubble will appear. So why bubble is appearing? Because we are blowing CO2 gas, we are blowing air in the form of CO2. Oh, sorry, we are blowing CO2 in the form of air, and air is not dissolving in water. That's why in the form of bubble from liquid, it it exit from the liquid in the air. Okay, so if we try to blow air in water, bubble will appear, because gases are not able to dissolve themselves in water or in liquid. But we can change this scenario by applying an artificial condition. How? We have an example of cold drink. When we open the cap of cold drink bottle, a sound of hiss appears. Why? Because whenever we open the cap, all the gases, all the CO2 gas will eliminate from this bottle, from bottle to air, right? Because we are decreasing the pressure. So what we can say, if we decrease the temperature, but if we increase the pressure, we can easily dissolve any kind of gas in liquid. Yes, and this methodology, or this uh, uh, concept was firstly proposed by scientist henry Henry. And this concept is called, or this law is called Henry's law. And what Henry said? Henry said that if we decrease the temperature, if we increase the pressure, we can easily dissolve the gas in liquid conditions, or we can say in solvents. And he also told one simple mathematical concept, that is partial pressure partial pressure of any gas is always directly proportional to the mole fraction of that gas. We have studied the mole fraction. So what is partial pressure? Every gas possesses a small quantity of gas or small quantity of pressure, which is called partial pressure. Okay, so you can see the law, that is partial pressure of gas in vapor phase is proportional to the mole fraction of gas in the solution. Okay, so we can say that P directly proportional to chi. We have to remove this proportionality symbol, and we are converting it into P is equals to kh into chi. And what is kh here? Kh is equals to Henry's constant. Henry's constant. Clear? So this is very important. This is we can say very essential law for defining the solubility of gases in liquid. Okay. Next, moving on to the next segment. So we have completed the definition, types, solubility, concentration terms. Now Raoult's law, very important law, Raoult's law. Now what Raoult's law says, look, we have to apply Raoult's law for what we can say, for solutes. There are two kind of solutes, everybody. that is volatile solute and non-volatile solute. Okay, so what Raoult's law says? Raoult's law says that for any solution, the partial pressure of each volatile component is directly proportional to its mole fraction. Suppose I'm rubbing this. Suppose we have component A, or we have a substance A. Substance A is showing some partial pressure P. So we can say it PA. So PA of A is always directly proportional to chi of A. This is called Raoult's law. So for any solution, the partial vapor pressure of each volatile component must be even volatile. Non-volatile component is not will be the applicable for the Raoult's law, right? I know that there are two kind of solute, that is volatile and non-volatile, but Raoult's law is completely depends on the volatile solvents or volatile components. Okay, so for any solution, the partial vapor pressure of each volatile component is directly proportional to its mole fraction. So this should be the mathematical expression. Now, do not obey. Non-ideal solutions do not obey the Raoult's law. And who obeys the Raoult's law? Obviously, ideal solution. A kid who is obeying all the orders from his or her parent, he should be an ideal kid, or ideal boy, ideal girl. But if he or she is not obeying the orders of his or her parent, then he should be non-ideal boy, non-ideal kid, right? Similarly, any solution which obeys Raoult's law, ideal solution; which do not obey the Raoult's law, non-ideal solution. Okay, so do not obey Raoult's non-ideal solution, and who obeys, that is ideal solution. If you want to remember the example, so the simple example of non-ideal solution, ideal solution is N-hexane and N-heptane. The simple formula of N-hexane is we know that alkane, so CnH2n plus 2. If value of N is 6, so C6H 12 14, C6H14 is hexane. Okay, now Raoult's law for non-ideal solutions having positive deviation and negative deviation. Suppose Raoult's law also told that if any solution is following the Raoult's law, it should be ideal, no doubt is there. But if any solution is not obeying the Raoult's law, it should be non-ideal. But is my law is relevant for those non-ideal solutions? The answer is yes, because we can explain the positive and negative deviations. Okay, negative deviations will show that kind of non-ideal solution having maximum boiling azeotrope. What is the meaning of azeotrope? The meaning of azeotrope is two solutions, two different components, whenever they mix together, the boiling point becomes equal. Suppose we have a substance A and we have substance B, and we are mixing A and B, and after mixing A and B, a new solution C is formed, and the boiling point of C is constant. Suppose the boiling point of A is 10 and boiling point of B is 20, and we are mixing A and B, so 10 plus 20 30. No, the boiling point appeared as 25 for both. So how can we separate them? We cannot separate them. That's why this kind of solution is called azeotropic solution. Okay, so azeotropic solution having maximum boiling point called maximum boiling azeotropes, and azeotropic solution having minimum boiling point is called minimum boiling azeotrope, as it is mentioned in this flowchart. Okay, so for maximum boiling azeotrope, delta X mix should be negative, delta V mix should be negative. Delta H means enthalpy change. of mixing, and delta V mix is volume change of mixing. Okay, so both should be negative. But for minimum boiling azeotrops, change of volume during mixing should be positive, and change of enthalpy during mixing, it should also be positive. Okay, so this is all about Raoult's law, a very simple law. If you understand the concept along with the questions, obviously you will solve all type of questions with Raoult's law. It's very simple law. Calculations are very less. The very positive thing is calculations are very low. Now let's move on to the colligative properties. Yes, colligative properties. Now, what colligative property is? Suppose we are mixing solute in solvent for making solution. If properties of solution completely depends on the properties of solute, then this property is called colligative properties. I'm repeating myself. If you are mixing solute in solvent and making solution, then if properties of solution is completely depends on the properties of solute only, then this kind of properties are called colligative properties. On the basis of colligative properties, on the basis of properties, colligative properties are categorized into 4 parts. Number 1, osmotic properties, in short we can say OP. Second, depression and freezing point, DFP. Number 3, elevation in boiling point, EBP. And number 4, relative lowering of vapor pressure, RLVP. Okay, the simple formula of osmotic pressure is pi is equals to CRT. C is concentration, R is gas constant, and T is temperature in Kelvin. Depression and freezing point, delta TF the symbol, KF into W2 into 1000, M2 into W1. W2 is weight of solute, W1 is weight of solvent, M2 is weight of molecular weight of solute, and Kf is obviously the constant value which will be given to you in the question. Similarly, elevation of boiling point, delta TB, the symbol, again KB into 1000 into W2, M2 into W1. RLVP, W2 into M1, W2 into M2 into W1, P01 minus P0 upon P01. So this formula you should remember from your side, because many numerical problems came from these formulas, right? So you have to practice more from the previous year questions. Please do refer previous year questions only. Don't confuse yourself by solving questions from other materials, other modules, because questions becomes very tough and sometimes irrelevant also. So if you practice PYQ questions, previous year questions, you will be benefited, and your confidence will be high, definitely, from other students. Now, the last but not the least, abnormal molecular mass. Now, firstly, we have to understand what is abnormal molecular mass. Suppose I am explaining this term in a very separate manner. Yeah, for example, suppose I have acetic acid. I have acetic acid, right? The formula of acetic acid is CH3COOH. Okay, now if we calculate the molecular weight of acetic acid, it should be 12 plus 3 plus 12 plus 16 plus 16 plus 1. Okay, for calculating the molecular weight, we have to add all the so we have to add the atomic weight of all the atoms, right? So 12 plus 3 plus 12 plus 16 plus 16 plus 1. Now 16 16 32, 33, 12, 12, 24 and 3. So 33, 24, 3, 60. So answer should be 60 gram. So what we can say? We can say that for acetic acid, molecular weight is 60 gram per mole. Clear? Now, there is one property in acetic acid called dimerization. This is a very unique property in all kind of acetic acids or acids having COOH group called dimerization. And what dimerization is, let me show you. Let me extend this page. Just wait. Yeah. The structure of COOH is something like this. Okay. Again, I am making another molecule of acetic acid. Something like this. Okay. Now we have two different molecules of acetic acid, but hydrogen is attracted by this oxygen and this hydrogen is attracted by this oxygen. So this kind of attraction is called hydrogen bonding. So due to the hydrogen bond, two molecules of acetic acid attach together, and after the attachment a cage like structure is formed which is called dimer. This is called dimer. Okay, so technically the molecular weight of acetic acid is 60 gram, right? But after dimerization, two molecules of acetic acid attached together. So 60 into 2, answer should be 120 gram. This is called abnormal molecular mass. Okay, so in reality the molecular weight of any molecule is fixed, but due to some special features its molecular weight changes, either increases or decreases. So this kind of abnormality in molecular weight is called abnormal molecular mass. Clear? Okay, so again we are yeah. Now to observe the abnormal molecular mass, as the definition, simple definition is written here. Abnormal molecular mass different from expected value due to some unique features, due to some special property, is called abnormal molecular mass. To calculate the abnormal molecular mass, we have a simple method called want of factor small I. And how can we calculate the want of factor? Normal molecular mass, abnormal molecular mass. Now, for example, for acetic acid, for CH3COOH, normal molecular mass of acetic acid is 60. We know that. And what should be that abnormal molecular mass after dimerization? 120. 120. So 1:2. Answer should be 0.5. So by these simple methods, we can easily calculate the abnormal molecular mass of any molecule having some special property. And this methodology is called want of factor method. Okay. Now, so we have completed all the subtopics to explain this chapter. Now, as I promised you, I'll practice some of the questions for you from the section concentration of solution. Right. So let me discuss one or two questions. Yeah. Okay. Now, question number 1. Calculate. You can pause the video and solve from yourself, and after that tell the answer from this lecture, right? So calculate the molarity of NaOH, of 40 gram NaOH dissolved in 1 liter solution. This is the question. Now pause the video and solve it. So I hope you have solved the question. Now let me tell you the answer. I'm changing my pen color, just wait. Yeah. Now to solve this question, we know the formula of molarity, as I discussed earlier in this lecture. Molarity, yeah, number of moles of solute, volume of solution. So we are using this formula. Okay, now the answer is, if we want to calculate the molarity, then we have to know the exact formula. So molarity is equal to moles by volume in liters. We have the volume in liter, that is 1, so no issue, but we don't have the moles. So to calculate the moles of NaOH, and listen carefully, if you want to calculate the moles, in 99% cases we have to calculate the moles of solute only, except in mole fraction. In mole fraction we have to calculate the moles of solute as well as for solvent, or all the components which is present in the solution. So moles of NaOH can be calculated as weight of NaOH upon molecular weight of NaOH. So weight of NaOH is given, that is 40 gram. And what is the molecular weight of NaOH? So what molecular weight of NaOH is, sodium is 23, oxygen is 16, hydrogen is 1. So it should be answer 40 gram. So 40 by 41. Now what should be molarity? 1 by 1 is equals to 1 m. Answer. Okay, so this is a very simple question, of course, but you can solve tougher questions by practicing these kind of simple questions. Obviously you have to make your level high on a daily basis. Simple, light, tough, moderate, tough, toughest, something like this. Okay, now question number 2. So I hope your answer and my answer is same. Okay, then this lecture is fruitful for you. Question number 2. Yeah, question number 2 is, calculate the weight of glucose in the 0.2 m aqueous solution having volume 2 liters. Okay, now pause the video and solve this. So I hope you have solved this question. Now let me solve this for you. This question is asking about the weight. It means W in grams of glucose. The chemical formula of glucose is C6H12O6. And what should be the molecular weight? Tell me. That is 180 grams. Okay, and we have the volume 2 liters, and we have the concentration. 0.2 m, and m is capital. Then we can say that molarity is given. So to solve this question, we have to apply the formula of molarity, because we have the concentration in molarity. So capital M, we know that moles upon volume in liters. Volume, we have the volume, that is 2. So forget it. Don't forget it. Forget it right now, only for right now. But we don't have the moles for glucose. So W glucose upon molecular weight of glucose, right? Now, if we use the formula, so capital M, so M is given, so we can say 0.2 is equals to, M is given, okay, I am writing here 0.2, okay, 0.2 is equals to moles. In the section of moles, we can write this expression. So W by M upon volume is given 2, okay. Now, so 0.2 into 2, this 2 is multiplied with 0.2, W by M. We know the molecular weight, that is 180. So 0.2 into 2 into 180, which can be multiplied with 0.2 into 2. So 180 is equals to W. So what should be the answer? The answer should be answer should be 10. So 18 fours are 72. W should be equal to 72 gram. So I hope your answer and my answer is same, because this question, the method of solving this question is like this, as you can see on your screens. Okay, now one last question, then we'll wrap up this lecture. Next question is, I'm changing my pen. Yeah, the last question is, find out the molality of sucrose. Find out the molality of sucrose if 3.42 gram sucrose dissolved in 400 ml of H2. So this is the question. Now pause the video and solve this. So I hope you have solved the question. Now let me solve this for you. Now according to this question, I have to solve the molality, not molarity, molality, and I have the weight of sucrose, and I have the volume of H2 also. Now to get the answer, I have to find out the molality, small m, I don't know that. Weight of sucrose is given, that is 3.42 grams, obviously. Molecular weight of sucrose is the formula of sucrose, C12H22O11. So it should be 12 into 12 plus 22 plus 11 into 16, 342 grams. And obviously we have volume of water, H2O, that is 400 ml. And remember that ml and gram are equivalent, not equal. Listen carefully, not equal, it is equivalent. Okay, so if I have 400 ml of water, then obviously I have 400 gram of water. So 400 gram, right? Now we know the formula of molality. Small m is equals to 3 moles upon weight in kg of solvent. So moles should be weight by molecular weight upon weight of kg, weight in kg of solvent, that is 400 ml, 400 grams, sorry, but it should be in kg, so 400 into 1000 the upper side. So 3.42 upon 342, it should be equal to 0.01. 20 cancel out into 10 by 4. So 4 ones are 4, point 4 twos are 8, 6 are remaining, sorry, 4 twos are 8, sorry, 4 twos are 8, 2 is remaining, 0.05, 0.5. Okay, so it should be, the answer should be, molarity should be 0.01 into 2.5. So 110. So answer should be 25 upon 123. So 0.025. This is the answer. Match it? Matched? Okay. So this is all about the chapter solution from the unit number 5 for your JEE syllabus. Okay, and you can see in this lecture, this chapter is completely for, not completely, 80% chapter is completely depends on the numerical part. Okay, so please do practice from previous year questions only. Don't bother, don't indulge yourself with materials of different coachings, modules and other materials, because they are very tough. Your confidence will go down if you solve those questions. So do solve previous year questions. They are very, those questions are made for students only, in a doable manner. Those questions are doable if you are applying your logic, your concept, your intelligence. The question will solve definitely. Okay, so do solve those questions, and do practice more, obviously. Okay, and we'll meet in some other lectures. Okay, thank you so much everybody. I hope this lecture is fruitful for you, and keep practicing, and motivate yourself. And thank you so much, and we'll meet in the next section. Thank you so much.